So it's come time to talk about electric fields. And the story of the electric field is a pretty good one. It goes back to a guy by the name of Michael Faraday. And Michael Faraday took over the Royal Institution, which was the official British science doing group. This is the group that would publish papers and endow exploration and all kinds of stuff. And basically just collect all the science that was done in Britain and elsewhere. And Michael Faraday got the job via a rather circuitous route. He was supposed to be a bookbinder, which is a reasonably blue-collar job to have in, Victorian England. But he got interested in science because they would have science lectures for free. This is back before TV and radio, so entertainment was where you could get it. And if they were putting on a lecture at the local, hall, you went and you watched and you learned. And he got fascinated with science. The problem is he didn't have the serious educational background, and in particular, he struggled with math. They say the same thing is true about Einstein, but I have my doubts as to the level at which he struggled with math. But anyway, Faraday really couldn't hack it, so he got very involved in doing electrical research because that was the sexy new stuff that was going on at the time. But he couldn't hack the working out Coulomb's law and figuring out the forces. So he was trying to find a way to imagine what was going on with the forces, and he came up with this idea of electric fields, which are lines representing the force. So he could visualize and draw pictures of what was going to happen and actually get some reasonable results out of these rules. So here's what you have to do to draw electric field lines. First of all, we have to introduce this idea of a test charge. Because what we're going to do is we're going to make a map of what's going on in a region. So a map of the force. So the test charge is an imaginary 1 Coulomb positive charge. And what you do is you place it in various places and ask what's going to happen to that guy. What's going to happen to him? What will he feel? Oh, I've assigned a gender to him. We don't know about the gender of the test charge, so maybe I'll use a different pronoun next time. So let's do that. Let's take this area on the paper and let's just say let's pretend we have something that's positively charged. Our conductor with our 5 coulombs of charge on it because I drew 5 positive things. And now let's imagine what happens when we put the imaginary test charge in various places. Okay, so if we were to put the imaginary test charge very close to this thing and above it, it would feel a tremendous force shooting away. If we were to put it over here but further away, it would feel a smaller force shooting away. Maybe we'll make it a little longer. There we go. And if we were to put it even further away, it would feel an even smaller force. So what we could do is we could draw a bunch of really long lines near the thing and then some shorter lines as you get further away and even shorter as you get further away. We could draw a whole bunch of lines and they'd all be going away from the central charge. But there's no rhyme or reason for these lines that I'm drawing. Oops, that one's too long. It's further away, so it should be shorter. And then tiny little lines out here, tiny little arrows. That's kind of complicated. So what Faraday said is, look, let's just take these lines and let's get rid of the individual vectorness of them, and let's just draw them as continuous lines and obey some rules. Let's just draw a whole bunch of radial lines going away from, well, I guess we do need to indicate the direction that they're going. They're away from, and then we'll draw some here. I'm putting one in between each of these, and what the hell, let's put one in between each of those, huh? I'm going crazy with my radial lines. We're going to draw a whole bunch of lines going away from this thing. Little arrowheads on them to indicate that it's going away. And now these arrows were big when you were close and small when you were far away. How do we recapture the idea of strong force when you're close and weak when you're far away? Well, we're going to take the density of lines. So this is low density lines. They're not very close together, and that would mean small force will be felt. And in here, these lines are high density lines. Therefore, that means high force. So electric field lines are lines that are drawn to show you what force an imaginary test charge would feel. And after a while, you don't even need the imaginary test charge to generate this idea, this map. You just kind of know how these things behave. And I'll tell you how they behave. There are some rules for electric field lines. And here are the rules. I'm going to abbreviate E field so I don't have to write out electric field. Number one, oh God, that's good. Number one, the lines go away from positive charge and toward negative charge. Number two, the lines never cross. The lines never cross because that would mean that at one place you felt two separate forces, but we know that when you feel two separate forces, we just have to combine those forces in a vector way to find out what the net force is. Number three, the lines curve smoothly. And number four, what we discovered is that the density of the lines implies the strength of the field or force. This is where the idea of a force field comes from, a field force field, or however you want to say it. You can actually mathematically recover the force from an electric field if you want to define it that way, and you'll see that there's an equation in your book for doing so. But I want us to keep this in the spirit of Michael Faraday and just draw the lines. So here's some situations that we can draw. If we had just a positive charge in space, we will draw one thing. If we had just a negative charge in space, we will draw another thing. And then what if we had a positive charge near a negative charge? So these are three separate drawings that they're not in the same space, okay? So positive charge by itself, we realize that you draw some radial lines away. I'm going to draw 8 lines going away. Now, in order to know that they're going away, we have to add a little arrowhead to each one. Practiced physicists leave the arrowheads off, but there you go. We're going to draw radial lines coming towards the negative charge. It seems like I missed one. Maybe not. Hey, this looks kind of like a snowflake. But as a learning physicist, you're going to have to show the arrowheads to show me that you know which way these lines go. What about this situation? Now, these are by themselves, too far apart to be interacting, but these are close together. This is something that we call a dipole. They're very common in the world of electricity and magnetism. A dipole, well, around each of these things, we would have the same field as we had when they were by themselves. When you're very close to one charge or the other, it's going to be dominating the landscape, dominating the forces that you feel. But in this region between them, that's interesting. But this is an arrow going away, and this is an arrow going towards, so it's kind of reasonable that we would connect them. And this one, probably, if you were to drop off a charge here, it would be repelled away from the positive charge. But then as it got away from the positive charge, it would be attracted to the negative charge. So I bet this bends over and is attracted over here. And I bet this one bends over and is attached here. And I bet this one goes around and is attached over here. And vice versa. This one probably goes and I get to make sound effects. What do we do with this one? Well, this one just goes off away from the world, and this one just comes in. Maybe these are connected at infinity, but the deal is if I dropped off a test charge here, it would be repelled away from this positive charge, and it would be shot away, but its attraction to the negative charge, it would never be able to act on that because the positive charge will always be closer in repelling it. So on this line, you're not going to get that. But if you moved over just a little bit over here, you'd be repelled away from the positive charge, and then eventually you'd get far enough away where maybe you could get around and get back to the negative charge the other way. But this is a dipole field. By the way, I like to call this like the onion drawing or the butterfly drawing. And it's pretty common in the world of science. In fact, this is the, if you were to drop a toaster in the bathtub with you, and it's not an electric field that we're dealing with then, it's a flow of current. That's what's going to kill you with that. But the toaster has a cord in it that has a positive and a negative right next to each other in the same cable. And this is what happens. And the actual flow of current is really strong between them, but it's these ones that go around the outside that if your leg was over here and you drop the toaster next to you, you might be part of this, and that's bad. But I think the Mythbusters did a thing that, you know, if you were to drop a toaster in the bathtub at the far end of the bathtub and not be in the same area of the bathtub, you might actually survive that, particularly if the toaster tripped a circuit breaker and turned it off fast enough. So what am I saying? I'm off on a tangent again. There we go. Welcome to Harmon's Physics. So that's what I wanted to say about the electric field. The electric field are lines. They represent the force that you would feel, and they give you a visual way to do science. And that's good for today.